This is AP Podcast 7.9, and we are going to talk about the Solubility Equilibria and Ksp. So the first thing, Ksp is just like every other equilibrium constant or expression that we've done. You do products over reactants. But what it does is it answers the question, will all of a solid dissolve? And if not, how much of it actually will? So we need to remember that when we're dealing with Ks of any sort, that is because of an equilibrium process that's going on. Dissolving is an equilibrium process. If there's not much solid, then a lot of it is going to dissolve, if not all of it will dissolve. And then the more solid that you add, the more the solution will become saturated. The solid will precipitate as fast as it dissolves, and that's that dynamic equilibrium process that we've talked about. So the rate of precipitation is the rate of the solid dissolving. Those are equal, and that's when it's reached an equilibrium. And then when no more solid will dissolve, the solution is said to be saturated. When we're writing these equations for the dissolving of solids, we want to take the solid and break it up into its cation and its anion. So the general equation that we use is we have our solid. We'll call it our metal and our nonmetal. And then my A and my B are the subscripts. When we write this out, so your metal is going to be the cation, the anion is going to be the nonmetal. When this breaks up, I guess I should probably put an S in there as well. When this breaks up, it's going to break into so many of the metal with some charge, and that's going to be aqueous, plus however many of the nonmetals we have, and then its charge. So we have our metal and our nonmetal. A's and B's are just subscripts, and then we just break it up into however many of each we have. The Ksp expression is going to be the products over the reactants. But in this case, it's going to be the products raised to the A power, and then the nonmetals raised to their power. Just like we did before, if there's a coefficient, that's what the power is here. And we don't include the reactants in this. Because the reactant is a solid and solids are said not to have a concentration, solids are not going to be included when we do these KSPs. That means it's only this product side where we have the ions that are going to be written into the KSP expression. We don't include the solid because its concentration doesn't change. It's the same reason that we don't include a liquid when we're doing equilibriums with other K values. All right, this one, example problem 1, says write the dissociation reaction and Ksp expression for each solid. So we're going to do what we just talked about. If I have calcium, I'm just going to go ahead and build off of this. It's my solid. I want to write the reaction first for how it will dissociate. There's one calcium, so calcium with its charge, aqueous, plus I have 2 fluoride ions, and they'll be aqueous. So that's the dissociation reaction for calcium fluoride. Then if I wanted to write its Ksp, I would just put the concentration of the calcium ions in square brackets, and I'd put the concentration of the fluoride ions, and I would want to square that one because of the coefficient out here. So that would be the end of the Ksp for letter A. Letter B, we'll do the same thing. I'll just throw a solid on the end there. This, though, is going to turn into 3 magnesium ions, and I have 2 of the phosphates. So there's the dissociation reaction for that one, and then the Ksp is going to be magnesium ions, and we are going to want to cube that, times the phosphate ions squared. So that's how you write these, and we're going to get a lot of practice with those with these example problems that we're going to do. So watch out when you're doing this and you're reading the problems that we're doing. You're going to see the word solubility and solubility product. They are not the same thing. When you see the term solubility product, it's talking about that equilibrium constant. It's talking about Ksp. So the solubility product is Ksp. When it says just solubility, it's talking about how much solid can dissolve. And this is a number that can be changed by a common ion. The solubility product, we know, just like every other K, is not changed unless the temperature changes. So with the solubility, some common units that they'll ask you to find are grams per liter and moles per liter. So really they're looking, this would be concentration. Grams per liter is another one you see, usually because we measure out solids in grams. So this is an easy way to see how much will go into a liter of water, so we can tell how much solid will actually dissolve. All right, we are getting into our example problems then. We just have several that we're going to go through together so you see what we're doing. The first problem here, example problem 2, says calculate the Ksp for the following solutions. Letter A wants the solubility of Fe, which would be iron, and the C2O4 is oxalate, so this is iron 2 oxalate. And what they're telling us is that the solubility is 65.9 milligrams per liter. What I'm going to do though first is, because when we try and do KSPs, we know that KSP deals with molarities, deals with concentrations. So the first thing I'm going to do is I'm going to take this number and I'm going to change it into moles per liter. So it's molarity, and that will help me get to my K. So I'm just going to do some dimensional analysis, some conversions here. And it's milligrams per liter. So there are 1,000 milligrams in a gram, and then if I add all of these up on the periodic table, it has a molar mass of 143.85 grams, and that's 1 mole of it. I went there so that I end up in moles per liter, which is a concentration, and that gives me 4.58 times 10 to the negative 4th molar. So I'm going to hang on to that for 1 second, and I'm going to write out what actually happens to this when I put it in water. What is the reaction for it dissolving? So we have the iron 2 oxalate, solid. You put it into water and you get 1 iron and 1 oxalate. So I know then that my expression is equal to the concentration of the iron ions times the concentration of these ions. And what we do is we think about, in terms of molarity, that if I have X number of moles of this, or molarity of this, I'm going to have X of that and X of that, because the coefficients are 1. If this were a 2, then this would become 2x. If this were a 3, then this would become 3x. But since they're both just one of each, the molarity of this is going to produce the molarity of that and the molarity of that. So if this is what dissolves, then we know it's going to split into the iron and the oxalate ions. I know that that's what my concentration is going to be of these two individual things. So that means that this is also equal to x squared, because I have x of this times x of this. Well, we know x. They told us this is equal to x. That is the solubility, which is what goes into these parentheses. So all I have to do to solve this is take 4.58 times 10 to the negative 4th, and I square it. And when I do that, that's my equilibrium, that's my solubility product. And the answer for that is 2.1 times 10 to the negative 7th. And there are no units on K, just like there have always been no units. So we went and took the solubility into concentration, and that was what we got to plug in to our KSP expression for X here. And we're going to do another one that's a little bit more complicated than that. So this says the solubility of lithium carbonate is 5.48 grams per liter. This is how much lithium carbonate will actually dissolve. Just like before, the first thing I'm going to do is I need to convert this into moles per liter. So I'm going to start grams per liter, And then I don't need to go to grams, I'm already there, so I just go right to the molar mass. Lithium carbonate's molar mass is 74 grams. I do the division, I'm left with moles per liter, which is good, I need a concentration. So this is 0.074 molar. I write out what lithium carbonate will do when it dissolves. It splits into 2 lithiums and, oops, there's an aqueous there, and 1 carbonate. So if we are thinking again, if this has a concentration of X, this is going to be then 2X, because for every one of these that breaks down, 2 of these form and 1 of these form. So I have 2X and X. This again is my X value. That's what I'm going to plug in here. So when I write my Ksp expression, I have the concentration of lithium ions, and I need to square it times the concentration of the carbonate ion, and it's just regular. So 2x, that would be 2 times 0.074, and that's going to be squared. That's x times 2, and then just a regular x goes right here. And all I do is find the answer to that. And when I do, what I find is the Ksp for lithium carbonate comes out as 1.62 times 10 to the negative third. So this one was just a little bit more complicated because we had to deal with coefficients. So 2x, because every one of these that goes in, we get 2 of those. And then your carbonate is x because there's only 1 of them. And making sure that you multiply x by whatever the coefficient is when you plug it in to calculate Ksp. All right, example problem 3 says what is the solubility of copper 1 bromide is 2 times 10 to the negative 4th molar. What is the solubility product? This again is asking us what we were just doing in example problem 2. We're trying to figure out what is Ksp. So we're looking for Ksp again. I would approach it the same way. If I wasn't in concentration already, which I am, I would convert, but this is nice because it's already there. So I'm going to start by writing out what this thing splits into. So it splits into copper ions, except that's copper 1, and bromide ions. So there's my reaction. If this is X, then this is X, then this is X, because there are no coefficients. And there's my X that they gave me in the problem. So Ksp is equal to the concentration of copper ions times the concentration of bromide ions, which equals X squared, because that's X and X, which is going to be 2 times 10 to the negative 4th squared. So Ksp for copper 1 bromide comes out as 4.0 times 10 to the negative 8th. Okay, example problem 4a. Calculate the solubility of strontium sulfate with a Ksp of 3.2 times 10 to the negative 7th in molarity and grams per liter. So the first thing I'm going to do, because we're working backwards now, they're giving us the Ksp, we need to go back to the solubility. The first thing I want to do is write out my reaction of what happens when strontium sulfate dissolves. So strontium sulfate, when it dissolves, gives you strontium ions and sulfate ions. And then based on this, if this is X, and this is X. So my Ksp, which I know is 3.2 times 10 to the negative 7th, is equal to the concentration of strontium ions times the concentration of sulfate ions. So that is X squared. All I do is take the square root of both sides, and I can find out that X is 5.7 times 10 to the negative 4th molar. That is one of my answers because they asked me for molarity and grams per liter. For the second part of that with grams per liter, I take the answer I got here and I just do some dimensional analysis to get it into the units I need. So that's moles per liter. And 1 mole, I go to the periodic table and I add up strontium sulfate, is 183.62 grams. And doing that, you end up with 0.105 grams per liter. And there's the two answers they were looking for. So in this one, we had to go backwards. We already knew the Ksp, we had to solve for what X was. All right, example problem 4b. Calculate the solubility again, this time of a different product with the Ksp of 9 times 10 to the negative 12th. So I'm going to take Ag2CrO4, silver chromate. I'm going to break it up into the 2 silvers and the 1 chromate. So if I look and treat this as X, this is going to be 2X and this is going to be X. Ksp is equal to 9.0 times 10 to the negative 12th, which is going to be equal to, in this case, the concentration of silver ions squared times the concentration of the chromate ions. When, if I use x's, that becomes 2x squared times x. So I do this, I solve for x, and I find that x is equal to 1.3 times 10 to the negative 4th molar. And I didn't have to go to another unit besides that one, so I am just finished once I find out what x is. Okay, last problem. What is the molar solubility of silver sulfide? So this one is asking for the molar solubility. It's not asking for the solubility product. So in this case, I'm looking for X. What is X in molarity? And they've given me the Ksp. So this is just like the problems that we did right before this. I'm going to write the reaction out first. This is going to split into 2 silvers and 1 sulfur. If this is X, this is 2X, and this is X. Ksp is equal to 1.6 times 10 to the negative 49th. That's equal to the silver ion concentration squared times the sulfide concentration, which, if I use these values with x's, is going to be 2x squared times x. It's just like the problem that we just did. You solve for x and we end up getting 3.4 times 10 to the negative 17th molar. So not very much of that is going to dissolve. That's a pretty small number, but we can tell that just by looking at the Ksp, because the Ksp is so tiny, it's to the negative 49th. That indicates that hardly any of this dissolves at all, and this would be considered insoluble because it basically stays as a solid. There's hardly any of these products over here where it's the ions. Okay, that is it. So knowing the difference between molarity and, not molarity, solubility and the solubility product is a big thing, and also understanding how you can use the solubility to calculate the solubility product, and just going back and forth between those things and writing out the reactions for how these solids dissolve. And we will do more practice with this in class.